Welcome to Learning Redis by Pact Publishing. My name is Scott Gagno, and I'll be leading you on an adventure into using the Redis data store in the best way possible, by creating a game. So let's check out what I've got in store for you and what you can expect to learn. This is video 1.1, the Learning Redis course overview. So in this video, I'll introduce myself and the course you're about to take. And then we'll jump right into talking about the game we'll be creating as we learn about using Redis in an actual application. I'll be giving you an introduction to this course. I'll first talk about what you should already know as you start the course to maximize your experience. I'll explain what you can expect to learn in this course and what you can do to get there. First, let me introduce myself. I am a professional programmer with over 20 years of programming experience in various languages including Smalltalk, Java, Ruby, and Node.js. I've worked with a wide range of backend data systems across the SQL, object, and NoSQL spectrum. In addition, I am proud to be an educator, having taught both online and in academic settings. And on occasion, I even work as an actor. We're going to be covering a lot of ground in a little time, so I'm expecting that you already have some background in JavaScript. You should know your way around a code editor of your choice and know how to use a command prompt on your machine. Node.js and Redis are available on nearly all platforms, but we won't be covering specific details and differences on each operating system, so you may need to be able to do a little investigation yourself if something goes wrong on your platform. But generally, if that happens, a quick search with Google or stackoverflow.com will clear things up pretty quickly for you. As you might expect in a course titled Learning Redis, we're going to concentrate on making sure you learn the basics of using Redis as a data store. We'll cover installing Redis and connecting to a Redis instance from the command line interface, the Redis CLI. We'll also cover how to store and retrieve information from the database, including some of the basic data structures available to us in Redis. And finally, we'll take advantage of the publish-subscribe capability of the system. Depending on your background, you may even learn a bit about Node.js. What are we going to do? Create a game. The most original and fun game ever. Okay, well maybe not, but it should be a fun way to learn about Redis. And we'll talk about the game in just a little bit. In the next video, we'll continue the course introduction with a look at our game requirements and design. Welcome back. So in this video, we're going to cover an overview of the game that we'll be building as we cover the Redis subject matter of the course. So let's look at our game requirements. Number one, and most importantly, our game must take advantage of the functions of Redis. That is, after all, what we're here to learn. Also, because this course isn't focused on graphical game creation, and we don't want to get distracted by superfluous code, a ground rule is that this game must be able to be played without a board. Next, as real-time games bring a lot of complexity with them, our game will be turn-based. Each turn, then, must be able to be easily scored, and of course we must be able to score the game as a whole. Finally, it should be easily detectable that the game has reached an ending point so we can declare a winner. So here are the rules. I've devised a simple word-based game that may seem fairly familiar to you if you've ever played Hasbro's game called Scrabble. It is similar, but it's not quite the same, so let's take a look at my rules. In this game, each player will be given a small tray of letter tiles drawn from a finite bag of tiles. During a turn, a player will make a word from the letters the player has available in his or her tray, but must also include the final letter from the previous player's word. Naturally, the first player has no such restriction. Once a player submits a valid word, the word is scored and saved, and the tiles that the player used will be replenished from the letter bag. Then, the next player plays a word, if possible. If any player cannot form a word, they may pass to the next player without playing. The game continues until a player plays all of the letters in the tray and there are no more letters in the bag to replenish their tray. Or, all players pass their turns because they have no words to play. At the end of the game, the players' scores are totaled from the sum of their plays, and a winner is declared as the top scorer. The name of the game is Word Fling. Now we have a viable game design. Of course, we won't embellish it too much, but it will be functional as a minimal viable framework of a game. Indeed, I hope that you will have ideas to improve it as we work, and we'll dig in to create something totally unique to you once you've completed this course. Meanwhile, in the next section, let's get started with Redis. Welcome back. Now that you know what's coming, let's get started. In this second set of videos, we're going to cover what you need to know about installing Redis or connecting to a hosted Redis, and how to use the Redis command line interface, or the Redis CLI. Video 2.1 is installation. In this video, we're going to take a look at how to install Redis. First off, let's take a look at what could be the easiest possible way for those of you that are OS X users. Homebrew is a package management system. It can automatically download, compile, and install applications with their dependencies for you. So let's install Homebrew. Here's the Homebrew site. And to install Homebrew, you see you simply run this Ruby command script. Copy it, paste it into your terminal. Now I got an error that I already have Homebrew installed. You should not get that error unless you do as well. If it asks you to install Xcode command line tools, you will need to say yes also. Once you have brew installed, installing Redis is as simple as executing brew install Redis. Again, I already have it installed, but you should get a different message. Now, one of the benefits of using an open database such as Redis is the availability of the source code. So an alternative to Homebrew on OS X, or if you're installing on a Linux or a Unix system, is to simply download the Redis source code and build it yourself. In fact, this is the approach that is detailed on the Redis.io website. You see here under download. As you can see, you have several options available to you, including downloading older versions or early releases, but generally you'll just want to use the latest stable version of Redis. Now if you look down the page just a little bit, you'll see that there is an installation section, and this shows a few commands to download and build Redis. So what we'll want to do is give this a try, and you can generally copy and paste these into your terminal. I'm going to do something a little bit different on my OS X box because I don't have wget. I'm going to do a similar thing using curl-o, but other than that, it's the same commands. So I would download Redis. Now that I have that downloaded, I would execute this command. And I'm just copying and pasting from their website. We're going to cd into the Redis, and then we can just do make. Obviously, you'll need to have the developer tools installed for this to work. Those are generally in Linux, you'll have them. In OS X, you can install them. All right, and now we have it installed. Now, the Redis project itself doesn't directly support Windows. However, Microsoft, with its Open Tech group, does. So those of you who use Windows should be covered in this. In your case, you'll want to clone their GitHub repo and use Visual Studio to build the Redis database. So you go to github.com/msopentech/Redis, and you'll see that their project is here. You would go ahead and clone this repo using git clone. The command is over here. You grab this URL, come into your directory, type git clone the Redis. If you don't have git, you'll need to make sure you have git installed. And then you would build the project. The information on that is also here. Down here into using how to build Redis using Visual Studio. You go to this website and download the Visual Studio community, and you should be able to get started from there. There's more information on this and how to get it up and running on Windows. So now that you've hopefully built Redis without any issues, you should be able to start it with a simple redis-server command. Note that by default it will create its database file in the same place from which you started. Therefore, I'd recommend always starting the database from the same folder or directory if you're not using a configuration file. Alternatively, if you start Redis server and specify a configuration file, you may set the database file name and location. So look to your Redis installation for the default config file that you can modify if you would like, or use either way. And it will likely be something like /user/local/etc or etc/redis.conf. I'll show you that. So I have user local etc redis conf. That's where all my configuration is. And if I want to start Redis server, I can specify that file. And I'm up and running. So at this point, you should have a working copy of Redis on your system. But if you can't get it working for some reason, you don't need to worry too much. There are other options. So in the next video, we'll take a look at an alternative to running Redis locally on your machine, and that is running Redis remotely on somebody else's server. Hopefully you have a database, a Redis database that you've already installed. But now we're going to go on to talking about connecting to a remote database. So in this video, we'll take a look at running Redis remotely. I'll show you a few of the many places that will host Redis for you. We'll walk through how to set up one of them and learn how to connect to a remote Redis instance from your local machine. But first, what does it mean to remotely run on Redis? Well, put simply, it just means that you'll be storing your data on another server. Instead of running a Redis server on your local machine, you will access your Redis data as a remote client over your local network or over the internet instead of as a local client. Now, of course, when running anything remotely, there are performance and data accessibility considerations, but that's an extensive topic that we really won't be able to do any justice to in this course. So the good news is, if you don't want to or can't run Redis yourself, there are plenty of places that will do it for you. Here is a partial list of places that specialize in hosted Redis. Although you could certainly install Redis on any hosted server you have, as we've already shown. If you don't already have a private server, you might want to consider an option like one of these. So selecting a provider for your production hosting is completely up to your requirements and preferences, and I can't specifically recommend or endorse any of them. But both Redis Labs, shown here, and Redis for You, shown here, offer a free option. So let's quickly walk through a typical setup. I'm going to pick Redis Labs. So we're going to click on Free Database, and you will want to fill in your information here. Once you do and agree to your terms, it will send you an email so you can log in. I already have a login, so I'm going to do that. And you should come to, once you are able to log in, to a site like this. Now, we want to create a new Redis subscription, and we're going to take a free one. Now we'll want to give it a resource name. So let's call it Learning Redis, and we'll give it a password. Great, now it says I have a Learning Redis database that is pending. So we'll wait for a moment. Now it might take a couple minutes, but eventually you'll get a status of OK. We want to click through, and we can see all the information about the database that's been provisioned for us. And all we really care about right now is this endpoint. We need this host name, which is everything before the colon, and we need the port, which is the number after the colon. So host name, port, and password are all necessary to connect to any Redis database. So we'll use these in the next video. And next up, we'll use the Redis command line interface to verify that we can connect to our Redis database, whether you installed it locally or are accessing a remote database. All right, video 2.3, the Redis CLI. Hey, it's time to make Redis work. So in this video, we're going to introduce one of the most basic and probably the most useful Redis tools, the Redis command line interface, or CLI. The Redis CLI is the quickest and easiest way to interact with your database. It allows you to interactively issue the same commands that you will ultimately use in your applications, and then see the results of those commands immediately on your console. And to start it, we just have to run Redis CLI. But before you start the Redis CLI, let's take a look at a couple of options that you may need. If you're not connecting to a local default settings database with no password, for example, if you set up a remote database like we did in the previous section, you'll now need to specify that hostname, port, and password you noted on the Redis CLI command line with the -h, -p, and -a options. And also note that while you can run Redis CLI as a shell and issue commands interactively, as we will, you also have the option to include the command when you invoke it and have Redis CLI issue the command to Redis, get the result, and exit immediately. And this can be very useful for shell scripting. Okay, in fact, let's give it a try and see if our own database is reachable. I'll just type in Redis CLI and ping. Now, ping is a command that is designed to see if a database is reachable. If it works, we should get a response that says pong. In this case, I'm not running a local Redis database. Now, if you were, you should get a pong response. But I'm going to go ahead and use the database that we set up in the last section, which is a remote database. Let's go ahead and Redis CLI. Now, I need to specify the command line. I need a host. And let's look at here. We'll take the host from Redis Labs that I set up. I need a port. And I need a password. Well, I connected. But what I really wanted to do was ping and get a pong. So there we go. You should see the same kind of response if you go through this process with your own database settings. If you don't, unfortunately, you'll need now to figure out why you can't reach your database. So here are a couple other basic non-data commands that you might use against your Redis database. If you don't specify the password on the command line, you can actually set it inside the shell using the auth command. Echo merely returns whatever you send to it. Select will change your database, and quit will exit the shell. Let's take a quick look at those two. So I'm going to connect back to my database. Oops. Actually, let's try the auth first. So now I'm connected. Now I want to say auth so that I can do things against my database. There, I've given it a password. It says OK. I can use the echo command to echo back what I tell it. Select will tell me, so I can select a database. I can select one, I only have one database. And of course, quit when I want to get out. So now you've seen how to install Redis. You've seen how to set up a remote Redis database with a hosting provider. And you've seen how to use the Redis CLI to connect to, verify, and issue some commands against a Redis database. So we've got all the tools that we need to get started. In the next section, we're going to learn how to store and access any data in Redis using basic keys and values. Section 3, keys and values. So now that we've been able to connect to our database that we've either installed or set up remotely, we're going to take a look at storing and retrieving strings in our database, and we're going to look at the reachability of data, which is a very important concept. So this is video 3.1, storing and retrieving strings. So in this video, you'll see what it means when Redis is referred to as a key value store, and how we can use Redis to store, retrieve, and perform some basic and maybe a little more advanced manipulations of the most basic data type that Redis understands, the string. So now the most important thing to note with Redis is that all data is stored in a database and accessed through identifiers called keys. A key then is nothing more than any string value of up to 512 megabytes in size, which is very large, although keep in mind that shorter keys are better performing than longer ones. And note that each database has its own set of keys and that you'll only connect to one database at a time. So there will be no conflict between them if you use the same keys in different databases. And finally, I'll just mention here that nearly all data commands, whether they operate on a single key or multiple keys, are actually atomic. That means they happen all at once and either succeed or fail completely. So let's talk about the basic data access commands. The first couple will no doubt be quite intuitive to you. You can simply set, get, or delete values by their keys. Also, we can do a get set, which will get a value and set a new value at the same time, and set NX, which actually allows you to set a value only if it doesn't already exist. NX actually stands for not existing. So let's take a look at those commands in the CLI. We're going to go back and connect again to our database. Remember, we did that in the last section. And we have a terminal. So I'm going to do a set command. I'm going to set name equal to Scott. So what this does is sets the key that's called name and the value of Scott. Oh, I'm sorry, I do need to auth. And I'll try that again. Okay, now we've set that value. Let's get it back out. As you'd expect, get retrieves the value that we just set. And we can delete that as well. It tells us that 1 was deleted. Now if we try to get it, there's nothing there. So let's try this. Let's get set name Scott. Well, it returns nil. That's what was there before. Now let's try get set name Nancy. Now we get Scott because we had just set Scott in that database slot, and now we've reset it with Nancy, but we got the old value, that's Scott. So let's try something else. Now let's try set NX. You remember that set NX only sets if it's not set. We get 0. And what 0 means here is that it changed nothing. If we do get name, we have Nancy. So now let's try delete name. Check again. It really is gone. And let's do the set NX to JSON again. Now we received 1, which means that it did do something. And if we get name, it is indeed JSON. Excellent. So now, of course, sometimes you'll want to change more than one value at once, either for performance reasons or to ensure that the changes are a single atomic action. They all happen at once and succeed or fail together. For these, there are the M commands. And they're exactly variations on the commands that you just used. mset, mget, msetNX work exactly the same as setget and setNX, except that you may provide more than one set of values to them. And by the way, delete actually by itself takes multiple values too, and there is no mdelete. So let's turn to a super useful tool that you can apply to your keys. Expiration. Being able to have your keys expire at a certain time or after a period of time is extremely useful when using database, for example, as a cache, or when you have data that becomes irrelevant and can be cleaned up automatically to save memory at a later time. The commands expire and expire at allow you to modify any key to be removed after a number of seconds, in the first case, expire, or at a certain time, expire at. Alternatively, for simple string values, you can actually use the setx command to set a value with a timestamp in a single command. Then, once the expiration has been set, the ttl command allows you to query that key for its expiration. And persist lets you delete the expiration time and then thus allowing the key to remain persistent. So let's play with that just a little bit. We still have a value in the name key of JSON, right? So we don't have to change that. Let's go ahead and say that we want to expire name in, well, let's make it quick, 10 seconds from now. All right, we got 1, that means it did something. Let's check its time to live. 3 seconds left, so give it a couple moments. TTL, oh, -2, so actually it has passed. Let's call get name, and it is gone. So it has expired and it's gone from the database. So finally, before we move on, I'd like to briefly mention a few more tricks Redis has up its sleeves. Using the INCR, or inc, so it's short for increment, or increment by, decrement, DECR, and decrement by operations, you can increase or decrease an integer value without having to retrieve the value first. This is super useful for counters, rate limiters, or other similar operations. The getRange and setRange commands allow you to retrieve or replace part of a string extremely efficiently. So remember that strings can be extremely large. So this can be useful in a number of situations where you might need to work with parts of a large string. And similarly, the bit operations allow you to access specific positions in a string value as if they were bits in a bit array. So it's a little more esoteric, and we're not really going to get into that. But just keep in mind, you can check it out on the Redis site if you want to look at the documentation. So next up, we'll be looking at storing, retrieving, and querying your data when all you have are keys and we have no indexes. Video 3.2, keys instead of indexes. In this video, we're going to talk about reachability in Redis and how to structure our database based on keys. We'll talk about some of the basic patterns we can use to keep our keys straight, and we'll understand how we can get some of the functionality that we would have had from indexes by using keys instead. So as you saw from our prior video, all data is accessed from Redis using keys. So it follows then, if there is no key, there is no value. Also, we saw when looking at expiring values in the last video that we can manipulate the lifetime of the values that we place in the database through their keys. So this is common across all Redis data types, be it a string, a list, set, hash, or any other type in Redis. Keys, however, don't simply exist in a vacuum. All keys in Redis are contained within a Redis database, which essentially defines a namespace for the keys. So when you connect to Redis, by default you're connecting to database 0, which we saw earlier, but you can use the command select to change between databases. The index value that you give it is really simply just an integer that is less than the configured maximum value of the databases, and this is just something that exists in your config. Now, within a database, you have several options of manipulating keys outside of simple storage and retrieval of values, like we saw. The simplest is the exists command, which, as you would completely expect, just tests for the existence of a key. You also have the ability to rename a key, But you have to be careful though. If you don't want to overwrite an existing target when you do your rename, you will want to use rename nx, which, like the other nx commands that you saw, will only rename a key if the target does not exist. So it will prevent you from overwriting something else. The keys command will return all the keys matching a pattern that you provide, and flushdb will delete all the keys from the database. But let's talk about defining keys. In general, you will want to create a specific schema and stick with it. You can define your own, but a common practice is to define your keys based on the type and attribute information of the object or the value being stored. For example, if you were to store your user in the database, you might choose to store it in a key that indicates, 1, that it is a user, and 2, that you access it by an ID. So as you can see in the example here, we do this by creating a key with the static values of user and ID, and the dynamic value of a unique ID that we've created for the user. And we separate all these by colons and represent the user value itself as a JSON string. Thus we can get or set the value in a way that mimics what a SQL query on the UUID might look like. So that you can't actually use that select star, but that's essentially what we're doing when we call get on the user :ID :1234. Now, of course, a consequence of not having indexes or a query language is that you are necessarily required to manage any secondary indexes yourself. What this means in practice is that for each path to a data structure you must build and maintain that path yourself. You have to define that reachability. If you have complex needs, this can mean that you might have to maintain several paths based on attributes, and each of these indexes must be kept in sync with your data. In fact, if you have many of these, you might want to reconsider whether Redis is the right store for this part of your data. So let's see why that is. We're going to take a simple example of accessing users by zip code. Now let's say I'm a fan of Beverly Hills, and I know that I at least want to find all 90210 users. So I create a new set of keys that use the schema that I already defined and contain user followed by zip code, and then the zip code the user is in. So user zip code 90210. Of course, there will be more than one, so this value will need to be in some sort of list or set. But now if I don't want to denormalize and store the complete user record in multiple places, each value in that set will have to be a key for the user from the primary index. And if I do that, then I'll just need to ensure that every time I add, change, or delete a user, I update this set. Once all that is done, I'll be able to access my 90210 users by getting the values from the secondary zip code index and then the values from the primary index. So to wrap up, a Redis database is a namespace defining a collection of keys. Those keys are strings that define the reachability of the data they are associated with. The keys can be created, deleted, and manipulated in many ways, but if you need to query and access your data in ways beyond your primary index, you'll need to maintain those indexes yourself. So I know we went through all of this very quickly, and it might be confusing still, but don't worry. We are going to be covering this well and several times in our game as we go along. So next up, the moment you've been waiting for, we're going to start coding that game. And a game's got to have players, so let's start there. Learning Redis, Section 4. A game needs players. Modeling a player. Okay folks, it's time to get our game started. And what's the first thing that every game needs? That's right, I've already given you the answer. Players. But see how easy this is going to be? Now in this section, we're going to be looking at creating a persistent model for a player, storing and retrieving the player data in Redis, and we'll spend some quality time on security namely the storing and validating those player passwords. Video 4.1, Modeling a Player. So now in this video, we're going to talk about what a player represents in our system, and then we'll talk about how we're going to model the persistent player data using Redis structures. Now the best place to start with modeling is determining just how much you actually need to model. We want to figure out the minimum necessary functionality of a player in our system. So let's walk through exactly what our game expects of a player. Now, we need to identify who's playing the game, right? So a player in our system needs to be able to register and log in. A player must also be able to start a new game or join a game that a player has created. And finally, a player needs to be able to submit a turn when appropriate, which also implies that we need to communicate with the user and tell them when it's time to take their turn. So now let's look at how a player relates to our application. Now clearly a player needs an ID and a password to be able to register and log in. A player also seems to need a set of games. But is that right? Or does a game need a set of players? Maybe both? Well, we'll need to consider that, but we're going to leave that for later. So now remember, with no indexes and queries, reachability is paramount. In this case, it makes sense that we should be able to reach these objects in the system by using some sort of an ID. In fact, let's just agree right now that a player's ID will be their email. If we identify players by their email addresses, we'll be able to avoid any additional lookup methods in the system. The user will be able to register with their email, and they'll log in with their email. A player will even be able to find their friends by email. So we probably won't need another method for finding friends. Likewise, by using an email ID, a player would be able to readily find their friends' games. So, we've defined our access key as player, the type player, plus the player's email address. So what are we storing in that key value? So in the case of the player, this is pretty straightforward. We just need to store a few strings to match our requirements. It's basically the player's email and their password. And let's go ahead and add a name field just so we can be a little more friendly. So all we're modeling here is actually a simple set of key value pairs. But fortunately, there's a Redis structure just for that kind of thing. It's called a hash. So we're going to use that. Now you might be wondering, why don't we just store the games in the player hash too? Well, for one thing, reachability. We'll need to access any given game in several ways, and only one of which is through a certain player. Now the most obvious one of which is that we have multiple players in any given game. So if we have an object accessible in multiple contexts, it must have its own identity separate from the player. Okay, so why not store the game ID on the player? Well, the player could be playing multiple games at the same time. So really, we need to have a set of games for each player. Now Redis has a set that we can use to store the game IDs, but we can't store it as a value in the player hash because that needs to be a string. So we'll just create a key that identifies a Redis set of games for a player, and we'll store the ID there. We'll see that later. So now we've defined our access keys and our model. So next up, let's write some code. We'll be creating, storing, and retrieving these players in no time at all. Learning Redis Video 4.2, Creating, Storing, and Retrieving Players. Now in our last video, we took a look at how we'd model a player in the game using Redis. In this video, we're going to get all of the tools that we're going to work with installed, including a Node.js skeleton app, learn how to run the tests that will be checking our work, and get into writing some of the Node.js code to bring it all together. Before we start writing code in Node.js, we need the Node.js runtime and npm, which is the Node package manager, installed. This is operating system specific, so I'm not going to spend much time on this, but the Node.js.org website has everything that you should need. I'll show you that right here. If you go to downloads, all the information is here. Next, we need to ensure that we have a package called Mocha installed so that you can run my tests, and I'll show you that in a second. And finally, you should install the Git version control tool. Now, technically, it's not absolutely necessary, as you could otherwise download the code as a zip file from GitHub, but it would be a lot easier to play along if you're just using Git. Now, if you've already installed Node or you believe you're ready to go, you can verify that your system works just by running node-v on your command line, and you should see a result similar to what I have there. Next, you want to be able to run npm-v. You should see a version number there as well. Now, you might not have these exact version numbers. That's fine. You might have version 0.10. something for Node or version 4. something for Node, and that's just fine. Next, we need to ensure that we have Mocha installed. Since we have npm, and we can see that, it's a very simple command. We do npm install-g, which means global, Mocha. After a moment, you should see something similar to what my screen displays. And once it does, you can verify by typing mocha --help, which should give you help information. In some cases, you might need to type sudo in front of that command, npm install-g mocha, because of security constraints. If so, you'll have to give an administrator password. So the next thing you'll need is the application code. Now I'm going to keep the amount of code minimal to make it as easy as possible on you, especially if you're not a Node.js expert. But I also want to give you a chance to participate. So I'll be including a lot of the non-Redis code so that you can follow along. And I'll be giving you unit tests that you can run to verify the code that you're writing is working properly every step of the way. Now let me show you how you can get the code. Since you have Git installed, you'll type in git clone https://github.com/wordfling.get. That will pull all the code down into a directory called wordfling. You can change into that directory, and then we'll just type get checkout 4.2 because that's the name of the chapter that we're on and the branch that we'll be using inside of Git. Now, as mentioned before, you can actually download the code from GitHub directly. You go to GitHub, the same address as what I use there. You're going to go to the branches, go to the correct branch that we're looking for, 4.2, and then we're going to download the zip. Once you have that, then you can extract it and gain access to the source code as well. Either way, once you have that skeleton and you're on the correct branch, just type in npm install so we can install the dependencies that we need, and we're ready to go. Now, one final thing before we look at the code. You're going to need to set your Redis configuration. So we're going to open the redis_config.js file in the config directory and set the host and the port to your Redis installation. So I'll show you in Redis config. What I have here is a local host and port. I don't need a password, but if you need a password, go ahead and delete this and put your password in there. And then a DB, and usually you can just use 0 there, and then you're done. Now, assuming that all has been installed and updated correctly, you should be able to run the word fling ping script that I've already included for you to verify that your application can access the database. So you just run bin / wordfling.js and type ping. Now we get a result that shows our configuration and that we get a result of Pong. So now we're ready to run the tests for this section of learning Redis. We're just going to execute mocha test /4.2. Again, that's our section in the command line. And we should see a couple of errors. Now, our test should be able to create a new player and retrieve it, but they can't. But this is actually okay. It's exactly what we expect, as we haven't completed the code for this section yet. But first, it's been a while. You remember our model? We decided that we'd store a player as a Redis hash. A Redis hash is just a set of key value pairs, just like Redis itself. The only difference is that we stored this set in a Redis key. So let's convert this model into JavaScript. Okay, now open the live player.js file in your favorite code editor, and you should see, if you look down, a couple of functions that need to be implemented. We have here create player and get player. So let's implement get player first because it's quick and easy. And I've already implemented a helper function for you here called make key that you can use. So to make a key, we just call that, set the key equals to make key and give it the email. And then we want to return the Redis hash. So we'll just do that using Redis. And this is the first time we'll actually get to call a Redis function here. And we call it just by using the same name as the command. So we're going to use hgetAll, which retrieves all of the values from a hash based on the key. And we're just going to return that to the caller, and that's what the little CB at the end means. Okay? And remember, you can look up any of the commands over at redis.io/commands. So hgetAll, you can see it gets all the fields of a hash. So let's go back to this. The other thing that we're going to want to do is the create player. Now I've listed out the steps here for you to create a player. We're going to call get player that we just wrote to see if the email already exists. If it does, we're going to return an error. Otherwise, we're going to create a player object. We're going to save the player, and then we'll return the player. So you can try to do that now if you want. I'm going to cheat a little bit here and grab this function already so we can go through it quickly without spending a lot of time on JavaScript. I'll show you what I'm doing here. We're going to call getPlayer, as I said. We're going to pass it the email, and it's going to return the player in a callback function. If there's an error, we get out. We return an error to the caller. If there's a player already, then we're going to return that error because we already have the player done. We can't create a player with the same email address. Otherwise, we're going to assign the player to this hash, which has an email, a name, and a password that was passed in. We're going to make the key, again, that we're going to save it in. We're going to use hmset, which sets a number of hash values at a key. We're going to give it the key that we created. We're going to give it the player hash that we created. We're going to check if it got an error. And if it didn't, then we're going to return the player. So we'll save that. And we're going to run our test again. And now you can see that we actually do pass our tests. So take a look back at that code a little bit more if you need to. If you're not familiar with Node, it may take a little bit of working with. Go ahead and feel free to play with it. As long as the tests run, you've got the right information. So now you can create and save a player in Redis. Hey, congratulations. But let's hold up a second. With all the issues we've seen in the press over security lately, I feel it's the responsible thing to do a small detour before we go on. So next up, we're going to talk about storing and validating passwords for login. This is video 4.3, Storing and Validating Passwords for Login. We're going to take a brief detour from Redis to talk about security in general, and specifically password security. We'll talk about how we can avoid storing passwords in our database and still validate that a user's name and password is correct when logging in. So there are just a couple of things I want to instill here. One, nothing is secure. No stored data in the world is completely secure. But that doesn't mean that you shouldn't try. Which leads us to number 2. The more sensitive the data, the more protection is required. If you're storing sensitive data, you must determine the amount of risk you are willing to take and take precautions appropriately. And number 3, never store passwords. Not only are passwords sensitive data, but they can more easily be protected than most data. So let's take a look at how. So a cryptographic hash function is essentially a one-way encryption device. This function allows us to take data and turn it into output that is practically impossible to turn back into the original data. So this is very useful in the case of storing passwords, as we can use this to take a password, hash it into a secure set of characters, and then store that without compromising the original user's password. Thus, even if our data was somehow to be compromised, the user's password would not be revealed, and the compromised password hash could still not be used to directly log into our system. So more complex password strategies can be defined, but at its core, the password strategy is really simple. 1, we want to be able to hash the password before we save a player. Thus, we will never store the password in our database. And number 2, when the user attempts to log in, we hash the password they give us and then compare that to the hash that we stored. If they match, it's the correct password and we can allow the user access. So I'm not going to spend much time on this as we're not covering Redis, but I'm going to show you a little bit of code so that we've changed the player a bit. If we look in player.js now, I've added a function called hash password. And what this does is it takes the player, it looks at the player password. If there is one, it uses a bcrypt library to hash that password. It returns a hash. We delete the player password. We add a player password hash, and then we return that value. And then the only other thing that needs to be done is in our save player, also a new function that I've added, we have a hash password, which calls this method that we just called, before it saves the player using the hmset command. Okay, enough about that. So in this section, we've modeled the game player as a hash structure in Redis and turned that code into Node.js that stores and retrieves the data. We've also looked into storing passwords, or actually why we don't store them, and how we can avoid it. In the next section, we're going to move on from players for a while. Next, we're going to discuss another interesting piece of the puzzle, creating a dictionary and validating the words in the game. Learning Redis, Section 5, Building a Word Dictionary. So this is going to be a fun little section. We're going to build a word dictionary in Redis and learn about Redis sets along the way. This is video 5.1, Sets and Membership. In this video, we're going to take a look at why we need a dictionary for our game in the first place, although this is probably already obvious to you, and what the capabilities of Redis set are, and how to use a Redis set to help us create an efficient dictionary. So why do we need a dictionary? Well, every time a user takes a turn, we need to validate that they have the letters that they are really trying to play, that the rules allow that play, and finally that the letters they are attempting to play make up a valid word. So we're going to deal with the first two later when we talk about taking a turn, but for now we need a way to validate a word against a dictionary. The perfect structure for this exists in Redis as a set. What is a set? Well, you can think of it as a bag of strings. The strings in the bag have no order, and the bag will contain no duplicates no matter how many times you add the same string to it. The key feature of a Redis set is extremely fast tests for membership. This allows a set to perform multi-set operations such as union and intersection, as well as simple is it in the set membership tests. So common use cases for a set are, say, friends lists and tags, and of course our dictionary. So let's take a quick look at a couple of the basic commands that we can use to interface with the set. As mentioned, a couple of key commands are adding members using sadd and determining membership using sIsMember. Both of these take the name of the set, which is your key, and the string member to add or check. The next command, smembers, retrieves all the members of the set. But remember that unlike a list, we generally don't need or want to iterate over the members, especially if there are a lot of them. And finally, scard allows you to get the cardinality, which is the size of a set's membership. So for even more fun, you can efficiently perform set arithmetic between two or more sets. Now you might remember from studying set theory, or maybe not, that there are three basic ways of combining sets. There's union, intersection, and difference. And these correspond to sunion, sinter, and sdiff Redis commands. And as you can see, I've included some nifty Venn diagram graphics that show you how they work. Of course, there are many more set commands, which you can see in the Redis documentation, but this gives you a good idea of how sets can be used. So, let's put our newfound set knowledge to work. In the next video, we're going to import a dictionary of words into Redis and put it to work. Video 5.2, Making a Redis Dictionary. In this video, we're going to find a dictionary to use, we're going to import it into Redis, and use it to determine if a word we give it is valid. Now, I can tell you right now that I don't want to type in all the words that are valid for our game. So step one for me is to find a dictionary that I can use. I'm also a working guy, so I really don't want to pay for a list of words. Nor do I want you to. Fortunately, after doing a bit of research, I found a couple of solutions that work for me in English, and I'm sure you can probably find similar for other languages if you need to. The first is the word dictionary that comes with most Unix-like systems. On OS X, this is located in the /user/share/dic/words file. I'll show you right here quickly. User share dic words. There's a file there that has all your words. For more options though, I also found a lovely website at wordlist.aspell.net. For English language again, this website is a fantastic resource for obtaining or even creating customized spelling dictionaries that contain American or British words at various levels of common usage. It's perfect for a game such as ours. The dictionaries offered here and generated by the site are, again, simply a file of line-delimited words, like the file I just showed you. Although in this case, each word is immediately followed by a slash and some sort of code on the same line. But we can easily just throw this extra information away as we parse the list and add the words to Redis. So find yourself a file, however you want, and let's import it. All we'll need to do is read the file line by line, parse off the extra information if necessary. We'll use sadd to add each word into Redis, and then we'll use scard on the set when we're done so we can see the number of words we've put into the dictionary. Okay, time to write some more code. But first, you have a choice each time we do advance to the next section of coding. Now I'll show you how to switch the code branch for this section in a second. It will remove all your edits and clean things up for making the code changes required in the section. Alternatively, you can ignore these instructions, keep your code so far, and try to keep pushing onward on your own. But in general, I'd recommend just doing a section at a time. But it's really up to your comfort level with coding and debugging Node.js. Okay, so if you're resetting your code base for this section, all you need to do is type in get checkout 5.2 and then use a new little option --force. And what this does is it ignores the fact that you've made changes and it will overwrite anything that you've done with the new branch. And so it'll reset everything for you. Okay. Now, either way, I've created a test for you again. So you want to run it with mocha test, and we're in 5.2 now. Once again, the tests should be broken. You just need to make it work. So let's focus on the first test first. We need to import the dictionary file. So we're going to open up live dictionary. We're going to edit that and look at the import file function, which is right here. Now I'll give you a quick rundown of what's happening here. So we're using a Node module called readline, which you can see here, that basically just reads a file in a line at a time. Each line it gets, it's going to call this onLine function, and we're going to do a little bit of work on the word so that we can add it in. We're going to call this add word function, which we'll write later. And then when it gets to the end, it'll call onClose. And on close, we need to go ahead and fill in the information to return the size of the set. So you can see I've tried to narrow things down so that you can just focus on the Redis commands themselves. And if you already have a good idea of where you're going, you can go ahead and try that now and see where you get. Otherwise, we're going to go ahead and step through this. So on close, remember we wanted to return the cardinality of the set. So we're going to call Redis scard, and we're going to return, or we're going to use this dictionary key that we have, and then return that to the caller. And then we, of course, need to add the word to the dictionary. So down here, we're going to call Redis sadd, set add, dictionary key. We'll add the word and return the result of that to the caller. So let's try running our tests again. Okay, we are importing the dictionary file and not validating. Right, so that's exactly correct. Now that we've imported the words, we need to determine if a word is valid. So this one's super easy because we have a command that does exactly what we want. Just remember that sIsMember returns a 1 if the string exists and a 0 if not. But our tests are going to expect a Boolean. So we're going to have to make sure that we convert the 0 or 1 into a Boolean value for our tests to work. So we go to isValidWord, and we're going to call Redis sIsMember. Once again, we give it a dictionary key. We give it a word, but we can't return that directly. So we're going to add a function here to give us the information. And what we're going to do is return the error if there is one, and otherwise we're going to return using bang bang result, basically turns a 0 into false or a 1 into true. So that should do it for us. Run our tests, and boy, if you've gotten here, you're golden and we can move on. So to summarize, we've learned that a Redis set is great for maintaining a collection that we need to do quick membership tests on, or that we need to perform arithmetic given 2 or more sets. Using this structure for our word dictionary was perfect, as it was simple to use and gives us constant performance regardless of set size, also known as O1 performance. Next up, we're going to investigate how we can break down a game as just a list of turns. Section 6, Modeling the Game. So now we're going to get into some serious modeling as we take on the game itself. In this section, we're going to model the game. We'll create, store, and retrieve the game model in Redis, and we'll also look at modeling a bag of game tiles, which, as you'll see, will be absolutely critical to our gameplay. Video 6.1, Understanding the Game. In this video, we'll need to dig into how users will interact with the game so we can understand the data access patterns. We'll also need to figure out what we actually need to track in the database as we move through the game. We'll need to gather all this information in order to create a usable design that works with Redis. To help us start developing our game model, let's look at what a game looks like from our player's point of view. So what steps do I take to start, play, and finish a game? Well, first, of course, I need to create a game with my friends. Now, once that game has started, at some point, I'll need to take a turn. Now, remember, the rules allow playing against the first or last letter of their word. So before I can take my turn, if I'm not first, I'll need to see the previous play to determine what letters are valid to play against. Okay, so now I look at my letter tray and try to form some good words. After much debate with myself, I finally choose a word to play, and I submit it. Now I draw new tiles to replace the ones that I just played for the next turn. And finally, at some point, I'll celebrate that I once again trounced my friends in a friendly game of word fling. So, wow, it's a lot of work to play a game. It seems we need to track a lot of stuff just to get to our sudden but inevitable win. But let's see how that looks as relationship. So you can see a game has a number of players, and each player has his or her own tray of letters. Now also, a game tracks the turns the player has taken, and of course each turn was played by a player. But actually, so that's not too bad. But once again, the key to Redis's heart is defining your access patterns or reachability. So let's look at how we'll reference these game objects as we move through the gameplay. Now, first of all, we need to create the game. There's not a game ID yet, but we do need the list of players that are going to play. And after we create the game, then we'll have a game ID. Next, we need to see what happened in the last turn. Now we could use the turn ID to do this, but we don't necessarily even know that. And it will be changing with each turn anyway, so it's easier just to use the game ID here as well, and figure it out from the list of turns. We need to check a player's tray of letters, so of course we'll need the game ID again, but now we'll also need a player ID. Then the player takes a turn, so game ID, player ID. Finally, the player needs to draw replacement letters, again, game ID and player ID. So can you see how the pattern breaks down here? Well, once we create the game, we'll use that game ID for accessing everything associated with the game. And in most cases, we'll also need to use the player ID to discriminate, as we do have multiple players associated with the game. So now we have enough information to quickly model our game. We need to limit the gameplay. So we're going to start by having a bag of letter tiles that we randomly draw from. This is probably a good use for a Redis set. In fact, it even has a method for random access. Next, we need to track the players. Another set? Well, no, because we also need to track the order of play. A Redis list maintains order, but we don't need this list anywhere outside of the game context. In fact, it would just complicate things to do so. We would have to look that up. So let's just store a serialized string of player IDs, an array, in the game hash. Speaking of which, we'll need to track whose turn it is, so we'll track the current player on the game as well. Now, each player also has a set of letters to select from in his or her tray, and I'm tempted to use a set again here, and that would be a fine choice, but in the future, I'd like to be nice to my players and allow them to rearrange the letters in their tray. So I'm going to go with a list, even if that means a little extra work on my part. And finally, we need to track all the turns that have been taken by the players. Since the turns happen in order, and each turn is fairly complex, we're going to store that as a list. So now we're good to start writing some code, and that's the subject for our next video, creating and storing a game. Video 6.2, creating and storing a game. In this video, we'll focus on our main object, the game. We'll work on creating, storing, and retrieving our basic game hash in Redis. So to get us started, let's take the information that we gathered in the last section and create a model that we can use for a game. Now, if you recall, we decided that many of the structures would be stored directly in the other Redis set or list structures, but that we had a few things that we wanted to store directly in the game hash. Now for that we need a unique ID for the game ID to access the game, and we'll need an array of player IDs and the current player index. So first, let's look at creating that unique ID. Remember when I mentioned the incr or increment command way back in section 3? Well, it's an atomic command that increments a value in the database and returns the next value. In other words, it's a counter. And a counter will work perfectly for a unique ID. Of course, we'll need a place to store this counter in Redis. So let's store it in the key game_ID_counter. So let's code it. So now we're going to set our branch to 6.2 in our code. If you recall, we do get, checkout, 6.2, and force to ensure that we have a clean slate. We're there. Now we want to run our tests, of course. Mocha test 6.2. And of course, it should fail. That's fine. So now we want to open up that game from our live directory. And we're going to take a look at that generate unique ID right down here, where it says use increment to generate a unique ID. This one should be completely straightforward for you if you want to give it a try. But here's what I'm going to do, redis.incr, and I have to pass it the game ID counter that I already have listed in the file, and then we're going to return the result to our caller. Okay, now let's go to the driving method, new game here. Here you'll see that we are creating a simple JavaScript object for the game containing the fields that we said that we needed to store in our hash. It's the ID, the player IDs, and the current player ID. There's nothing unusual here. We're just accepting the player IDs from the calling method as an array of strings, and we're using a random number generator basically to just pick one as the current player before we call save game. So let's look at save game. So as before, we need to call a makeKey function to create a Redis string for our key. Now remember, it's just a game colon the game ID. And we'll just use HMSet, the hash multiple set, to set all the fields in the JavaScript hash into our database. Now the conversion from JavaScript to Redis will happen automatically. And in fact, even the string array will be automatically converted to a comma delimited string for us. And now that said, when we retrieve the player IDs, we'll have to remember it won't create an array from the string because it doesn't know it should. So we'll have to look at that next. So let's do that here. We want first set up the game key, and we're going to do make key and just give it the game ID. And now that we have a key, we're going to go ahead and call Redis HMSet, that game key that we just created, tells it where to store it, and the game, and then we'll return it to the caller. So now let's look at the getGame function. To retrieve a Redis hash, remember that we use the hgetAll command. Now the JavaScript library will automatically load all the Redis values at the key into a JavaScript hash for us. Then we just need to finish the job. So there's two things that we'll do. One, we need to parse the player ID string into an array of strings. Now we can do that with a simple split call using the comma as a parameter. And two, we'll change the current player index from a string to an integer so that we can use it to reference the current player from the array we just created. So let's take a look at how that works. Now once again, I'm just going to copy this line because we have to do the same thing. We have to create a key. Then we're going to do Redis hgetAll using that game key. And then we're going to have a function that takes the result of that so that we can work with it. Now that we have that, we have to check if there's an error. We want to return the error immediately and stop. But if there's not, then we're going to do that split. So we're going to take the game, take the player IDs, and we're going to reassign them, game, player IDs, and we're going to split those. We need to split those on the comma. The next thing we want is to set that current player index equal to, and we're going to call parseInt, which is a JavaScript function that just turns game current player index into an integer. After that, we just need to return the results. We have no error, but we do want to return our game. Okay, save that. Let's go back now and run our tests again. And now you should see that all three tests are passing. So great job so far. Next up, we'll create the bag of tiles that the players will draw from as the game progresses. Video 6.3, the tile bag. In this video, we'll look at how we intend to model the tile bag, and then we'll go ahead and put it into the code. The tile bag is quite simple. We need a structure to store all the tiles that a player can use in the game. This is basically just the alphabet, but we'll also have several letters that can be used more than once, so we'll need to account for that. So we'll just use a Redis set to store our tiles. Besides just being a convenient structure for a bunch of unordered things like our tiles, this will also give us a very nice benefit of being able to grab random tiles from the bag just by using the Redis spop command. Now, of course, to do this, we can't just store the letters. The Redis set would remove any duplicates, and that's not what we want. Instead, we'll store each tile as being a letter plus a counter. That way, Redis will maintain them all, and we'll just have to remember to discard the count when we retrieve one to use as a letter. Okay, so here's a challenge for you if you feel adventurous. We're going to go ahead and check out branch 6.3 and run Mocha test 6.3. Now you should see 4 errors. Your challenge then is to open up the tile bag file, and when you do, you'll be able to go through the file and locate the places that have to-do items that you can go ahead and fill in the correct thing for Redis. And each one of them will describe exactly what you need to do. So go ahead and do that if you want, and then run the Mocha tests again to make sure that you've done the correct thing. Okay, so we're going to start with the create tile bag function. As we discussed, each letter in the letter frequencies table has a frequency associated with it. So we'll know to add that letter that many times to the database set. The sadd Redis command is used to add an item to the set, but in fact, we can use the sadd command to add all the tiles in an array in one command. So what I've done here is I've created an array with all of the letter tiles that we want to add, and all we need to do then here is go ahead and add those to Redis. So we're going to call Redis sadd. We're going to give it the key that we have above here. We're going to give it the tiles, and then we're going to return the result. It's very simple. Now we need a function to draw a tile from the set. So let's look at the function draw tile. As mentioned earlier, we'll use the spop command. Now this function pops or retrieves and removes a random element from a set. Now this is exactly what we want when we draw a tile from the bag. We want to pick a random tile. But there's just one more thing that we have to do here before we do that. We'll want to only return the letter part of what we stored, not the counter. Remember, we're adding a letter and a counter stored in this value. So we're just going to take the first character of the return string, which is our letter, and drop the frequency portion. So let's see how we do that. So first of all, we need to go ahead and call the Redis spop to get the value that we want. And we're going to use the bag key, and then we're going to use the function callback that we want here to retrieve the actual tile. Okay. Now, of course, as always, if there's an error, we want to return that error and get out. Now, if there's not, we need to assign the letter portion of the tile. So if there's a tile, we're going to take the tile 0, which is the first character of that tile value. Otherwise, we're going to have null, and then we're going to return no error, but we're going to return our letter. Okay? One final thing, we need to deal with tiles remaining. We need a function to determine if we indeed have tiles left. So this is super easy because cardinality is also one of the commands that you have in Redis. So we can literally just call Redis with the scard command, set cardinality, give it the key, and return the callback. So that should be all we need to do. So give it a save. We'll return here, run our tests again, and we have 4 passing tests. So We've made great strides in this section, actually. We've now modeled our game and can create, store, and retrieve it and associated players. We now have a tile bag, which will drive all of our players' turns. But speaking of turns, we're nearly ready to have players start taking those turns. So next up, taking a turn. Section 7, taking turns. Now that we have a game structure, we need to focus on how the game is played. In this section, we'll start by modeling the player's trays. That is, the player's hand where they hold the letters that they can use. Next, we'll look at validating the player's turn, ensuring that it meets our rules. And finally, we'll store the player's turns as part of the game. This is video 7.1, the player's trays. Now this video will break down the modeling of players' trays and how they will play the letters that they've been dealt. We'll look at how we create and refill a tray after the player plays the letters and how to determine that the letters from the tray are appropriate to form a given word. So to get to the meat of what needs to be done for this to work, let's break down a player's turn step by step. Now when the game starts, all the players are given a tray with 7 tiles. Each player looks at the letters in their tray and determines what word, in combination with the first and last letter of the previously played word, they can make, and decides to play that word. The word is checked against the dictionary and determined to be valid or not. If valid, the word is played, the tray is refilled to 7 tiles if possible, and play is passed to the next player. So let's throw out all the stuff that doesn't directly affect the tray. We're left with the following requirements. 1. The tray starts with and attempts to maintain 7 letters. 2. The tray must determine if a set of letters for a word exists in the tray. And 3. The tray's letters may be ordered by the player. Actually, so I just added that last one because I've played games like this and I know that players like to arrange and rearrange their letters as they attempt to form words. So we'll just call that one a user experience requirement, even though we aren't going to code that part in the video. Still, that last requirement is what forces us to use a list instead of a set, and that makes our task just slightly more difficult. Now, as usual, before we begin, we're going to check out the appropriate section, which we are in 7.1. We should go ahead and run our tests. So let's run test 7.1 and verify that we are indeed failing our tests. And we can see there the things that we'll need to do. Now let's open up tray. So the first thing we're going to do is create a tray. And, frankly, this actually couldn't be easier. Why? Because we're just going to delegate all the work to the refill tray method. After all, creating a tray is really the same thing as refilling a tray. That is, it pulls enough tiles from the tile bag to have a total of 7 in the list. So let's just do that. Let's just call refill tray, which I already have elsewhere. And we need to give it the same parameters that we had. And then we're done with that. Unfortunately, that won't fix any of our tests for us, but we'll pick up that function in just a minute. So now let's take a look at the play letters function here. This is the function that will drive the rest of the functionality of the tray. So now when a user chooses a set of letters to play, this function will be called. And as you can see, the first thing it needs to do is get the list of letters the player has from Redis. Here. So we're going to write that function next. But once it has the letters, it can call canPlayLetters to check that the letters played are a subset of the letters retrieved. And it does that here. So if that's correct, we attempt to remove all the letters from the player's tray. Here. And you see we're doing a remove here, a list remove. Now, you have to note that this is done using the Redis multi command here, which what that does is it just allows us to run multiple commands in the same transaction, so we can do it all at once. But then finally, after we execute that, we want to do the refill tray, the same function that we just talked about. So let's go ahead and write that get letters function that we need. So this function just needs to return the letters that we have in the tray. Now, I've already provided the make key method that creates the game :player ID string that we're using. So we just have to call a function using that key to retrieve all the letters in the list. So let's take a look through the list of list commands. Now, Redis, you'll notice, doesn't provide a function that returns all the elements in a list anywhere. This is crazy, right? Well, maybe not, because depending on the application, that could be a very large list of items that would be an expensive set to retrieve. Instead, Redis provides a function called lrange that allows us to retrieve a list of items. Notice that lrange takes three parameters. It takes the key, the start position, and the end position. Now, we want all the letters in our tray, so we'll specify 0 to start and max tiles, which is 7, as the end. So let's do that here. We have our tray key, so we're just going to call Redis lrange tray key 0, max tiles, and return it to the caller. Okay. So while we skipped doing this work while writing the create tray function, we knew we'd have to come back to the refill tray function for it to work, and now's the time. What we need to do here should be pretty obvious though. We need to calculate the number of tiles that we need and then draw them from the tile bag. We'll then take those letters and we'll add them to our tray. So let's do it. Let's go back to our tray.js. In the refill tray function here. Now the first thing we need to do, as always, we'll create the Redis key for our tray, and that's already here. It's called tray key. So now we want to find the length of the tray as it is right now, so we can calculate how many tiles we'll need to draw and replenish the tray from. So let's do that. Let's call Redis list length ln tray key. And this function is going to return our length to us. Now, as usual, we want to get rid of any errors that occur, return those to our caller. Now, I'm going to call this demand. Demand is basically the max number of tiles that we can have in our tray minus the length that we already have. And that will tell us how many we need. Now, if our demand is less than 1, we're basically going to get out. And what we're going to do is return an empty list of tiles to our caller. Basically, that's for testing, so that I can tell how many tiles were actually drawn. Now, we're going to go to the tile bag. We need to draw the tiles that we want. We're going to pass in game ID. We're going to pass in demand, telling it how many tiles to draw. And then it is going to return those tiles to us. As usual, you know what comes next. Turn those errors. Now we have the tiles, and the natural thing that we have to do is put them in the tray. So we're going to call the Redis lpush, list push. We're going to give it the tray key. We're going to give it the tiles that we want to push on there. And we're returning to the client. And that's basically it. So save that. Now we should be able to run our command to test. We get all 4 tests passing, which is fantastic. If you don't, once again, be sure to work through the errors before continuing so you understand what's going on. So, great job. Next up, We'll process and validate a player's turn. Video 7.2, Validating a Turn. Now in this video, we're going to look at ensuring that the words played by our players meet our requirements. We'll also look back at our game rules and add the code necessary to ensure that all plays are valid. So let's review our game rules as they stand. We need to ensure that all words actually exist in the dictionary that we've created. 2, all words must be played from the letters contained in the player's tray. 3, all words must use the first or last letter of the previous play, if any. By the way, the rules have been kept almost ridiculously simple, as the point of this class isn't to build a complex game, but rather to learn about how we might adapt the concepts of an application to Redis. So feel free to embellish the rules later as you wish to create your own variation of the game. But for now, let's go ahead and implement a function that enforces our rules. Okay, checkout. Use get checkout for branch 7.2. And we're going to go ahead and open up the game.js file in the live directory. So we're going to write a function called playWord, which is down around line 161. So this playWord function is passed a game ID, player ID, and a word. And its job is to return an error if the word doesn't abide by the rules. So the first part is super simple. We've already done the work. All we have to do is call into dictionary into the isValidWord function to find out if the word is in the dictionary. So literally, we can take this, we call dictionary isValidWord, we pass the word, returns a function, again, which gives us an error or and the word is word, which is a Boolean. So if error, as always, we return the error. If it's not a word, so it checked and told us that it's not a word, what we want to do is return a different error. In fact, we're going to use a function called makeError that I have, and you can check that out later if you want. But basically, it's just going to create an error, errors dot not a word is the error. If it's not a word, we'll send an error and quit. Now expect that no matter what the rules, we'll probably always want to do this, right? But the second part is we need to break out into another function. That way we can focus on just those rules. And if we decide to change the rules later, we can just easily modify the check against rules function. We'll just call that function with the same parameters as this function, and because we're not sure which letters will have to be used from the tray, we'll have it return those letters. So let's write that one. Let's just call check against rules. Again, we don't know what it's going to do, but we do know it's going to need the same information. It's going to return an error, and we're going to say it's going to return the letters to actually play. Now inside that, we check if there's an error, we return the error, and we tell the tray to go ahead and play the letters out of the tray that we just decided were okay to play. Great. Okay, now we're going to look at the check against rules function. Now, none of this function has anything to do with Redis, so I'm going to go over it fairly quickly, and you can review it later if you like. But we're not going to go ahead and write it. I'm just going to review it. Now, the first thing that we need here is the letters in the player's tray. Now, since we have the tray getLetters function, and we already wrote that. We'll just call it. Also, we need the last turn. So we actually don't have a function for that yet, but we're going to assume that we do and write it later. We know that the only thing it will need is a game ID. So we'll call it with that parameter and have it return the turn, the last turn. Now we have everything that we need to check our rules. Letters of the word, the letters in our tray, and the previous last turn, if there is one. So let's run down the rules. 1, if there's no last turn, we can just check if we can make the word from the tray. If we can, we return the word. If we can't, we return an error. 2, if there is a last turn, we need to check the first letter to see if we can make a word using that letter plus the letters of our tray. If we can, we return the letters used. And then we do the same with the last letter. Finally, if we haven't yet made a valid play, we just return an error. All done. Oh, wait. That's right, we have to implement that getLastTurn function I just mentioned. Okay, if you look around line 250 or so, you should find the function getLastTurn. Fortunately, we can let Redis do the work on this one, but we're going to have to cheat a little bit because we're not actually creating any turns yet. But don't worry, we're going to do that in the next video. But for now, we're going to assume that a list of turns already exists in Redis under the key created by the makeTurnKey function. Then, since that's the case, we'll just need to retrieve the last item from that list. Now, Redis has just the thing, the lindex command returns an item from a list at a specified index. So we could get the length of the list using the length command, and then call lindex with that. But better yet, Redis allows us to pass a negative number to the lindex command to return items counting backwards from the end. In other words, we can use -1 to get the last item, -2 to get the penultimate item, etc. So fantastic. So actually, we're just going to call another function that we're going to create, that you can see just under this, called getTurn, and we're going to pass it a -1. So we're going to call getTurn. We're going to give it the game ID. We're going to turn -1. That's going to return the last turn once we write this one. So in the getTurn function, all we have to do is call Redis lindex. We're going to give it the turn key and the index that's passed in. It's going to, of course, have an error and reply. You know this part. Then we're going to get the turn itself. So the turn is actually going to be stored as a JSON string. So we're going to have to convert it. And then we're going to return it. And that's it. So let's go ahead and save that. Now we're going to run our tests for 7.2. Looks like I made an error at game 171. Yes, I did. I said game and not game ID. Let's go back, try again. Another error, the same one. I had little typos here. Letters to play, not letter to play. And one more time, and we have passing tests. Very good. So next up, we'll stop cheating and really store the game turns. Video 7.3, Storing the Turn in the Game. In this video, we'll perform the core game functions of storing players' turns in a list, rotating play between players, ensuring that players can only play when it is their turn, and allowing players to skip a turn. So we already know that we'll be storing turns in a Redis list. So now we just need to nail down what we'll be storing in each turn. And actually, it's pretty simple. We'll store the ID of the player that took the turn, the word that they played, and the score that the game awarded them. Now technically, we might be able to get by without storing the score because we could calculate that from the word. But this is more efficient and a better log of what really happened in the game, just in case we decide to change the scoring algorithm for whatever reason. So let's take a look at the save turn function. As usual, we need to start by checking out the 7.3 branch and running the tests, of course. We should get errors. And then we're going to open up game.js in the lib directory and take a look at that. Now let's look for save turn. And you should see that on around line 194. So we're going to create the object from the parameters passed in. You can see we have player ID, word, and score here. Then we're going to make a key, turn the JavaScript object into a string so that we can store it in Redis. Then we're going to store it in Redis. Recall that a Redis list has lpush and rpush, depending on if you want to push the entry onto the head or the tail of the list. We want to push r's onto the tail end, so we'll use rpush. Now this is kind of starting to feel easy, right? So once we've saved our turn, we'll want to move to the next player. So let's go ahead and put in a call to advanced player function and code that as well. So save turn. We're going to take what we have. We want to do Redis, r, push, turn key, the string version of the turn that we created. This is going to return an error, if there is one, of course. If error, return CB error, as usual. And I'm going to copy that because we're going to use that again. Now we're going to call advanced player and give it the game ID. It's going to return either an error or the current player. Yeah, if I could only type, huh? All right. Again, the error check. And finally, we'll return the turn to the caller. There we go. So now, to advance the player, we just need to update the current player index. Let's take a look at advanced player. You can see on line 113 or thereabouts. So to advance the player, we just need to update the current player index part of our game. Now remember that unlike the turn, we're storing that as a JSON string. The game itself is a Redis hash. So we can access and update any value in it directly using a key. Now that said, there are a couple values we want to retrieve from the game, so I'm just going to grab the entire game to work on for this. So we'll call get game ID, function return an error or a game. Of course, we'll do our error check. Now that we have the game, all we need to do is calculate the next player based on the current player index and the number of players. Then we can update the current player index field directly without touching any of the others using the hset Redis command that allows us to specify the key and value we want to update in a hash, and we'll be done. So let's do that here. So we need to set the next player index equal to the game current player index and add 1 to that. Now, if the next player index is equal to the player ID's length, we're going to reset it to 0 because it has to wrap around to the first player. Now we want to get a game key because we're going to update that object in Redis. Redis hset, we're going to give it the key. We want to update the current player index value with our next player index. This is going to return an error potentially. And we're going to return that error and game player ID's next player index. So that returns the error and the next player ID. So let's track back to the take turn function right up here. Now you can see that all we need to do to take a turn is we need to get the game. We need to ensure that it's the correct player or an error. We need to play the word, calculate the score, and then save the turn. Seems like a lot of work, but actually it's not too bad. So let's go ahead and take our turn. Let's get the game. Return the game for us. Error check, of course. Now, if the game player IDs game current player index is not equal to the player ID, we're going to return and make an error saying that, sorry, it's not your turn. That should make sense. Okay. Now we can assume that it is the person's turn, and we can say we want to play the word, and we give it the game ID, the player ID, the word to be played, and of course it can potentially return an error, so we'll check that. Finally, the score. Now we ask the tile bag to score the word because we know it's a valid word and we know it's going to be played, and we're going to save turn and give it the game ID, the player ID, the word, the score, and return the results of all that. So I hope that makes sense. So let's go ahead and do one more. Let's add the skip turn as well. In this one, it actually is quite a bit easier. All we need to do is get the game, ensure it's the right player, and save the turn with no word and 0 score. So let's walk through it again. I could copy and paste, but I'm going to go ahead and type it out. We're going to get the game again, right? Check the error. Now, if the game player IDs, and remember we just did this, we're just checking to see if it's the right player is playing. So if you are the current player, you're okay. If you're not, we're going to go ahead and make that error. I'll spell that correctly. We're going to make error, error, not your turn. And if you are the correct player and you're skipping your turn, we'll go ahead and save your turn, game ID, your player ID, null for the word, 0 for your score, and we're done. Now you can guess what's next. Let's run those tests. And I made a mistake. Game 129. Oh, here. Error is not defined. 107. Sorry, it's errors. And it'll be errors here as well. Excellent. There we go. A little quick debugging and we've got it all working. So in this section, we did a lot of work with lists actually. In creating and using a tray as well as the list of turns, we learned how we can select a range of items from a list as well as retrieving specific elements from the list by index. We also learned how to add elements to the beginning or the end of a list. And finally, we updated a specific element of our Redis game hash, the current player index, using the hset command. So we now have pretty much an entire working game. Winning! Speaking of which, our next challenge is to determine the winners and losers. Welcome to Learning Redis, Section 8, Winners and Losers. So having now set up our implementation using Redis lists to track the players' trays and turns, we're getting very close to finishing our game. We just have a few more elements to take care of. In this section, we'll learn about the sorted set. We'll figure out how we can determine if a game has ended and who won, and we'll implement a game leaderboard that can display our top 10 players. But to have a social game, we're going to need a leaderboard that tracks those high scores. So let's look into how a sorted set in Redis works and figure out how we can use that structure to our advantage here. Video 8.1, how does a sorted set work? In this video, we'll look at the Redis sorted set structure. I'll introduce the structure, we'll talk about how it's used, and then we'll see how it could be applied to a game leaderboard. Now, you've already been introduced to a Redis set. As we learned, a set has a few basic constraints. Its elements are strings, which are unique throughout the set, and the elements are unordered. We use this property of set to provide a randomized bag of tiles to draw from. But now we're going to look at the Redis sorted set. It retains most of the properties of a set, but adds a twist. Unlike a set, a sorted set is ordered by a floating point score value that you associate with the element when it's inserted. And unlike a Redis list, which merely maintains the order of item insertion, forcing us to determine the order, the sorted set will always maintain the elements in ascending order based on the scores that we associate with them. So let's look at the basic commands you have available on a sorted set. Some of them, like zadd, zrem for remove, and zcard for cardinality, those will look familiar from using the set before. The only real difference is, with zadd, you now need to specify a score. Similarly, there is a z-score that retrieves the score associated with that member. There are a couple new tricks here though, dealing with rank and count. Now rank is the position of an element in the sorted list. If the element is at the front of the list, in other words has the lowest score, it will have a rank of 0. If it's at the end, it will be equal to the number of cardinality of the list minus 1. Conversely, using zrev rank, we'll reverse the rankings and assign rank 0 to the highest score. Finally, zcount will retrieve the number of elements that exist between the min and max scores specified. So let's look quickly at a couple of those commands in context in the Redis CLI. I'll create a sorted list that has the names and numbers 1 through 5 and assigns each one a score equal to the numeric value of that number. Okay, we'll assign 1, 1, 2, 2, 3, 3, 4, 4, 5 to 5. Okay, now let's look at Z card of the numbers, and as expected, we have 5 elements. Also, if we Z score the element called 4, Redis returns our score of 4. But now if we Z rank that same element, we see that we have a 3. Can you care to guess what the Z reverse rank of element 4 is? Z rev rank. Well, if you guessed 1, you were correct. It is the second element after 5 in the reverse ranked order, so the rank is actually 1. Now one more thing. What will we get if we get the Z count with a minimum of 2 and a maximum of 3? Aha, it's inclusive by default, so we get 2. If you want exclusive, you just need to add an open parenthesis to the min or max to exclude. So let's actually add it to our max, the element 3, and Redis will now tell us that we have just one element greater than or equal to 2, but less than 3. So that's pretty cool, right? But there's some even more valuable stuff you can do with sorted sets. You can work with ranges. Now Redis gives you the ability to query and manipulate ranges using scores and rank, and in some cases lexical information, but we're not going to cover these cases here. Z-range and Z-rev range allow you to query your set by rank position and optionally include the scores of the elements returned. Now likewise, Z-range by score and Z-range by rev score allow you to do range queries by score. And Z-rem range by rank and Z-rem range by score enable you to remove a range of elements in a similar manner by rank or score. So let's drop back into the Redis CLI and take a quick look at some of those commands. Now let's say we need to get the top 3 highest numbers in our set. So we can call zrev range numbers 0 to 2 with scores. And you can see that that will give us the highest ranked number to the third highest ranked number and include each element's score. So the elements and scores are 5, 4, and 3. So we have a high score list. Now that really does seem useful in the context of a game, doesn't it? But now let's say that we don't care about any scores below 3. Now we can throw them all away with the zrem range by score command, right? But first, let's check it out. Let's issue the command zrange by score, numbers 0 and less than 3. Yes, indeed, that selects scores 1 and 2, which, we don't care about at all. So let's issue the real command, zrem range by score numbers 0 less than 3. It returns 2, which means it deleted 2 records as expected. So now let's look at everything left in our set by using zrange by score numbers negative infinity to positive infinity. That will give us everything, and indeed 3, 4, and 5 are left. Perfect. Okay, now that we've covered the basics of sorted sets and how they differ from a standard Redis set, let's get back to the game and get it finished and scored. So next up, finishing the game. Hey, welcome back to Learning Redis. This is video 8.2, finishing the game and scoring. In our last video, we talked about sorted sets in anticipation of implementing a leaderboard for our game. But we're not quite ready for that. We need to finish the game first. In this video, we're going to take a look at detecting the end of the game and declaring the game over so we'll be able to score it. Now at this point, we need to decide what determines a game over for our game. We're going to keep it as simple as possible and declare two end of game scenarios. One, a player has no more tiles. That is, he or she has used the last of his tiles to play a word and the tile bag is empty, so no more tiles can be drawn. This is often called going out of the game. Number two, all players may skip their turns. Now this rule assumes that if a player skips his or her turn, it's because he or she cannot figure out a word to play, and no other player can make a play, so we're back to where we started. So the game is over. So let's look at some code. Now we're going to check out 8.2 and run our tests. We should get errors. Awesome. Now let's go ahead and jump into the game.js file. We're going to find the save turn function. And you should find it at about line 214. Now I've added a bit of code since when you've seen it before. So we're going to take a look at that. But basically what's happened now is that we're going to check for game over here. Now if that returns true, we're going to call the game over function. Otherwise, we're going to continue to call advanced player and calculate scores as we did before. So now let's look at that check for game over function. You'll find check for game over around line 264. Now this function is super simple. We'll just call the functions that repeat the rules that we decided on. Did the last player go out? Here? Yes. If he did, the game is over. If not, we'll just check, have all the players skipped? If that's the case, the game is over also. So it's quick and easy. And let's keep digging and move to the did last player go out function. Now we're still not writing any Redis code, so I'm just going to walk through this. And we're only calling functions that we already wrote. We need to call getLastTurn to get the last turn taken. So that way we know what player took their turn, and then we'll check his or her tray, so that if the player's tray is empty at this point, the player went out and the game is over. Now the other function that we called was to determine if all players have skipped their turns, because that would also indicate the end of the game. So we want to check here the last n number of turns, where n is equal to the number of players. Now as we did with the lindex command before, we'll expect that we can count backward from the end of the list using negative numbers. So we pass the number of players times -1 and -1 as our two parameters. And this will give us what we want. Each of the turns taken by our players in the last round. Now once we have that list of turns, we just have to make sure that all the players have actually had a chance to take a turn. That is, the number of turns taken is actually greater than the number of players. And then finally, we need to check each turn to see if the player played or skipped. If even one player played, we don't end the game. But if none did, yeah, it's game over. Now, let's get that getTurns function done. You should find this on line 319 or thereabouts. Now this should be pretty easy to understand now that it's essentially code that we've written before. So if you take a look, we need to use lrange to retrieve the requested turns. We need to parse it to turn the turns into objects. And then we need to return the list of objects. So let's do that. We're going to call Redis lrange, give it the turn key, a start, the end that were passed in. In our function, we have error, and it's going to return those turns as strings. you know the next thing. If error, return it. Now, let's take and assign our actual turns. We're going to use a function called map, which will basically just allow us to convert each one of our turns by calling JSON parse on it. And then all we have to do is return that. Very simple. So now let's look at game over. In our game over function, we just need to set the active flag to false. Then calculate the final scores, and we'll look at that in the next section. We'll set the game scores and save the game. Of course, we have a little more to do later, including setting the leaderboard, notifying players that the game is over, which we'll also do later. But so let's just do this part here. As it says, we need to get the game using the game ID. Return the error as usual. And then all we have to do is say game active equals false, and then save the game again. Now you'll notice that I'm not setting it directly using the Redis commands. That's because we're going to be doing more here later. As I said, we'll be calculating the scores and setting the score on the game, things like that. So instead, we're going to load and save the entire game. Oh, actually, there's one more thing. Because now we're saving extra things that aren't strings in the game, we need to adjust the save and load functions. Now, actually, in this case, we've only added the active flag, which will actually save just fine. The Boolean will be converted to a string for us. However, to load it, we'll need to change it back to a Boolean, which we have to do here in the getGame function. And this can be done very simply by resetting game active equal to game.active equal to the string true. Okay, that should be it. Let's save, run our test, and hopefully, we do have an error. String turn is not defined in 336. 336 string turn. Indeed, it's string turns. And in fact, I made the same mistake over here. This should be turns as well. So let's save that and run it. And now we're passing. Excellent. Okay, so that's it. At this point, we've now defined the entire game from beginning to end. And there's only one more thing to do. Let's score the game and store those results. Welcome to video 8.3, Scoring and Storing the Results. In this video, we'll look at how we can determine the final scores of the game and store them for future reference. Now, as usual, we're going to keep things as simple as possible. In this case, the scoring will be a simple matter of tallying up all the scores of the players throughout the game. Now, if you're familiar with other similar games, you might notice that we're not giving out bonuses or deductions for going out or having tiles left in the tray. Feel free to add these later, but for now we're going to skip that. Thus our scoring will be simply to retrieve all the turns, group them by player, sum their scores, and store the results on the game. So let's get started. You know the drill. Let's check out branch 8.3 and run those tests. Great, so our tests are failing. Now let's open up the game.js file again and look for the calculate scores function. You should find it around 323. The first thing that we do is call the function that we created in the last section, getTurns. As you recall, it calls lRange pretty much directly, so we pass in the same beginning and ending parameters here. By passing in 0 and -1, we specify that we want everything in the list, from first to last. Now the next step that we take is to group the turns by player ID. We do this to more easily sum the scores by player. Now, for each of the players and their associated turns, we have to sum up the scores from those turns. Now to do this, we're using a function called reduce that allows us to iterate over each of the turns and accumulate the total of the associated scores. That total is saved to the final scores associated with the appropriate player. So let's go back up here to the game over function. Now we're going to take the response from the calculate scores and assign it to the game scores property so that it can be saved to the database. So let's do that first. Let's call calculate scores, give it the game ID. It's going to return, let's go, an error or scores. As always, if there's an error, we'll return it. But if there's not, we're going to say game scores equal to the scores. Then we need to save the game. So we're going to move this up here so that we can save the game after we've set the scores. Great. But once again, we're storing something other than just a string. So let's go fix that part. If we go to the save game function, we can see that the scores of the game need to be converted to a string here. That's actually pretty easy. But we do want to check and make sure that there are scores first. Otherwise, we won't be converting anything. If there are, then we want to say the game scores are actually equal to the JSON string of the game scores. And that way we'll actually store it as a string instead of attempting to store the object. Then obviously, when we retrieve it, we have to do the same thing. We have to convert it back. So here, if we have game scores, we need to make sure that we convert it by using JSON parse the string back into an object. Fantastic, that's pretty easy. So let's go ahead and see if we can verify that. Running into typos, 164, right, we need to end the function here. Let's save it, run again, we're passing. So now we have the entire game being played and we're calculating the scores at the end. Nice work. So next up, we're going to figure out the top 10 players of all time. Welcome to Learning Redis, video 8.4, displaying the top 10 players. In this video, we'll create a game leaderboard and add the game scores to it. We'll see how we can maintain the size of the leaderboard so it doesn't grow without bounds. And finally, we'll see how to retrieve the top players given our criteria. Now, as we discussed in section 8.1, a sorted set is the perfect structure to maintain a leaderboard, so we're going to use that. Also, for now, we're just tracking the top scores of all time, so we'll keep a leaderboard called top scorers, and just save the player ID in it. Obviously, you might find other statistics interesting and add them later, but this is going to do for now. So code time. So do git checkout 8.4, and we'll run our tests. All right, we have a failing test. First, let's take a quick look at the game.js. Now, if you take a look at the game over function, around line 304, go down a little bit and you're going to see at line 321, I added a little function for you that calls leaderboard add scores. Well, we haven't done any of that work yet, so that's what we're going to do now. So let's open leaderboard.js in your live directory. So first of all, let's write a function for adding the scores to the Redis sorted set. Now, as usual, we make the key for Redis. Then we need to make the parameters to add the values to the sorted set. If you remember, the zadd function took a key and a score, followed by the associated member, followed by another score, followed by another member, and so on. Thus, the easiest thing for us to do here is to just build that command. Just add all the scores and player IDs from the scores that were just passed. So we can start by creating the params array with the key we want, since that's the first parameter, and then add all the scores in by just pushing them onto the array. And then once we have that array, we can just call the zadd function. So let's take a look at how that works. So first we're going to create our params array. We'll start it off with just the value of key, because that's the first parameter. Now we'll take object keys scores, which takes all of the player IDs, and for each of those player IDs, we're going to get the score of that player. And then we're going to take that params that we're going to push to Redis. We're going to put the score on there, because that's the first item. And then we're going to put the player ID on there, because that's the next item. Now once we've created that parameter list, we're going to call Redis zadd, use those parameters. Of course, it can return an error. If it's an error, we get out. But if it's not, we're going to want to call this next function called trim to size. We're going to give it the top scores size that we've already created, that's 10. And so what that does is allows us to keep the size of our leaderboard down. So we're going to trim it down to the top 10 every time. That way we don't have this list of things growing unbounded. And by the way, we could and probably should do trimming of the other lists we've made in our database too, but I'll leave that up to you. So let's take a look at that trim to size method. This is going to be super simple because it's entirely handled by Redis. Now in the last section we saw that we can call the Redis zrem range by rank command, and that removes a range of set elements based on their ordering. Zrem range by rank, we'll give it the key, and then we'll give it -1000 as a good place to start. If you remember, that means the 1000th highest score. And then we're going to take on up to the size that we want. Again, times -1 to ensure that it's counting the highest scores, not the lowest scores. And so that means that we're going to keep everything only up to the size that we've specified. Okay, so we have one more function that we need to worry about here. And that is, we need a function to return the top players. So we're going to query the Redis sorted set using the zrev range, using the with scores option. So we're going to grab all the scores between 0, the highest score, and n-1, which is the nth highest score. Now we know that using zrev range with the with scores option will return a list of strings. And those strings alternate between the elements, which is the player IDs, and the scores. But that's not quite as friendly as we could be. So instead, let's return an array where each element of the array is an object that has a player ID value and a score value. So to do that, we're going to iterate over the Redis results. We're going to create one element for each player ID and score pair and add that element to our results array. And also, while we're doing that, we have to remember not to forget to change the score into a number. So let's do that. So let's first create our results array. Now we're going to call Redis zRev range, give it the key 0, give it n-1, and we want the with scores option. Now that can return an error, but hopefully it's going to return our players and scores. If there is an error, we want to return that error. Great. Now, here's where the fun begins. We're going to iterate over these players and scores. And we're going to do it 2 at a time, because we want to process each player and score together. So we're going to set the player ID equal to the players and scores I, and we're going to set the score equal to players I plus 1, the next one. Then we're just going to push that onto our results. We're going to push an object that has a player ID equal to the player ID and score equal to, and remember, we have to parse the integer of score out of the string. Excellent. Then we just need to return that value. All right, save that and let's see how we're doing here. Let's go and try that. Couple of players and, player and scores. That's not correct. I should definitely have, there it is, players and scores. 69 result not defined. Should all be results. Excellent. Now, that was a lot, but honestly, that wasn't too bad given the amount of functionality we just added. In this section, we've seen just how a sorted set works and used it for setting up a game leaderboard. In addition, we finalized the game mechanics so that we could determine the end of the game and calculate game scores. So next up, we'll find a way to ensure that we can notify our players that, hey, it's your turn, or perhaps that they've lost and won't be taking any more turns. Next up, is it my turn yet? Welcome back to Learning Redis, Section 9, Is It My Turn? You know, we're almost to the end. We've finished all of the game mechanics, calculated the end of the game and the players' scores, and even created a leaderboard. But we haven't yet included a way to inform a player that it's his or her turn, or that the game has ended. So let's look into how Redis events can solve our problem. In this section, we'll ensure that we understand how Redis events work, we'll model our events, publish the events, and subscribe to the events in a complete end-to-end lifecycle. Video 9.1, Redis events. Now, frankly, there are many ways we could inform players that it's their turn. We could have just built it into the code like we've been doing with the other functions. But Redis has a really cool way to handle reactive functionality that works even between Redis clients that I think is worth exploring. So in this video, I'll quickly explain the publish-subscribe concept of events, and then we'll move right into how Redis implements it and how we can use it in our application. Publish-subscribe, also referred to as pub/sub, is a method of communication that decouples the sender of a message from the receiver by the use of named channels of communication. Now you can think of this as a broadcast, like radio or a television signal on a channel. A broadcaster or publisher sends a program out on a channel, and a person who wishes to receive the program, or a subscriber, just needs to tune to that channel to receive it. Note that the publisher doesn't need to register all of the receivers. It just sends out the data on the channel. Likewise, the subscriber doesn't need to know who is publishing the information, just which channels may include data that the client is interested in so that it can subscribe to them and evaluate the data being sent. Redis supports publish subscribe pretty much exactly as you might expect. The basic commands for this are subscribe, unsubscribe, and publish. To listen or stop listening to a channel, one uses subscribe or unsubscribe and includes the name or names of the channel or channels. Similarly, a publisher needs only to use the publish command with the name of the channel and a string message to send to any and all subscribers. It's a very simple but very powerful communication method that can be used not only in single applications, but also in distributed applications that are connected to the same Redis database. So let's take a look at how this works through the Redis CLI. We'll subscribe to a couple of channels that we'll just call test and test2. So let's start that up first. So let's subscribe to test and test2 using the subscribe command. Now notice that we immediately receive one message for each subscription, letting us know that we've subscribed to those channels. Also note that in the CLI, we can no longer issue commands on this connection. Now real clients like Node will operate differently and can still issue commands to Redis, but even in those cases, it's not allowed for a client once subscribed to issue commands other than to subscribe to additional channels or unsubscribe from them. Now let's open another Redis CLI window so we can see the other side. In this window, we'll publish a hello world message to the test channel. Publish test. Hello world. When we do this, we receive 1 as a confirmation that it was sent. So let's do the same for our channel test2. Excellent. So now let's switch back to our subscriber. Aha! Now things have changed over here. Now we see that after the subscribe events, we have 2 messages. In each case, we see 1, the text message indicating that a message was received on the channel. 2, the channel the message was received on, either test or test2. And 3, the message itself, in our case, hello world. It's super simple, right? Now, by the way, you can also subscribe or unsubscribe to multiple channels at a time using simple patterns. Much like you would pass a pattern to the keys command to select which keys to show, with psubscribe or punsubscribe, you can use the same pattern matching to select which channel's events you will receive. So, for example, let's kill this client that's subscribing right now and restart the CLI. And now we'll issue a new command to psubscribe to the asterisk. In other words, this will subscribe to all channels. Now, let's go to our other client, and we'll issue another hello world message on test2. Take a look now. This time the channel received 4 pieces of information. 1, the p message indicator. 2, the pattern we specified. 3, the channel. And 4, the message itself. Also notice that we didn't receive any of the old messages. It's important to realize that the channels are ephemeral, and only the subscribers who are actually active at the time of publishing will receive a published message. Now that you understand publish subscribe and how Redis events work, let's apply them to our game. Next up, modeling the event. Video 9.2, modeling the event. In the last video, we saw how to manipulate events in Redis through the CLI. Now we'll take a look at how we can use this functionality to communicate significant game events to our players and decide on a way to model it in our application. So let's consider for a moment if we hadn't decided to use pub/sub. What are our options and why aren't they as good? The first thing that comes to mind is just sending an email to the player. We're already using email as the ID. Why not just send them an email? Well, what if users are playing live and interactively? Email wouldn't really fit there. And even if not, the players might have different communications preferences for text notification, for example, or instant messaging. Also, what about the other listeners? What if other players want to watch the game? Then we'd need a way to register who's watching the game and notify them as well, which sounds a lot like a pub sub channel anyway, doesn't it? So let's get back to that. So let's look at the places where game changes state and players need to be informed. Well, we have start and end game and on each turn. In all cases, we'll want to identify the game. In fact, let's make that the channel name, so a player can just subscribe to the ones he or she cares about. Also, let's include the last play and all the scores, since it's pretty likely that the subscriber will want to see that. In most cases, we'll also need to identify whose turn it is, so we'll include that as well. And if we don't have a current player, we can assume that the game is finished. This sounds good enough for us right now. We could always expand or tune it later if needed. Okay, we've got a plan. Let's write some code. So next up, publishing the event. Video 9.3, Publishing the Events. In the last video, we decided on a module and strategy for using Redis's events to communicate with our players and potentially spectators. In this video, we'll take that strategy and apply it as code that publishes our events to the channel and add the hooks to integrate the publishing into the game. So let's jump in. Check out branch 9.3 and run the tests. Great. Now open the publish.js file. We'll start with the new game event publisher. First of all, as you can see, we've created a method that we can reuse for the channel ID. Channels are exactly like any other key in Redis. It's just a string identifier. However, pub/sub channel names don't conflict with entity names in Redis. Redis won't get them confused, so we don't have to worry about that. So we can just use the same makeKey function as we did for our keys, and we'll even call our channel game::game ID as we've used before without any concern. Now to the message. And remember we said that each game message would have a set of player scores, the current player ID, and the last turn. Well, in the case of a new game, we don't have any scores or turns, so we'll just accept the game ID, the player IDs, and the current player ID. Then we'll just create the player scores from the player IDs. We'll set each score to 0. Once we've done that, we create the message from the scores we just created and the current player, publish it as JSON string on the channel, and we'll be done. So let's do that. Let's go ahead and create our structure, player scores. Now for each player ID, we're going to set the player scores for that player ID equals to 0. Now let's create our message. Our message is going to be an event. We're going to send a new game event. It's going to be the player scores, which we just created. And it's going to be the current player, which we were passed. Okay. Now we just need a channel to send it on. It's the game channel is what I used for that method name, game ID. And we're going to call Redis publish on that channel the string version of the message that we just created. And we'll send it back to the callback. So next up is end turn. Now this one will be really easy because the caller should have everything that we need already. So we accept game ID, turn, player scores, and current player ID as our parameters. Then all we need to do is create the message object, get the channel name, and publish the JSON string to the channel. So let's go ahead and do that. Let's create the message object. So in this one, everything other than the event itself is passed to us. We'll create an event called endTurn. We'll set our player scores to the player scores that were passed to us. Our current player is the current player ID, and last turn is the turn that was sent to us. Excellent. Now actually we can just take the exact same code that we used up here. We're going to get the game channel, and then we'll publish our message to that channel. So finally, we need an end game. This time we don't have a current player since the game is over, but we're going to accept game ID, last turn, and the player scores. Now once again, this one's very simple. We'll just create the message object with what we have, and we'll leave out what we don't. So the message has player scores and last turn. We'll get the channel, stringify the JSON, and publish the message, and we'll be done. So our message here is going to be end game. Our player scores were passed in, and our last turn was passed. Very simply. Once again, we will send the message on the channel that we have. Fantastic. So we'll be moving on. Next up, we'll want to modify the saveTurn function to publish that we just ended a turn in the game. So we're going to have to go back and we're going to have to edit the game. Okay, great. Let's move to the new game function and take care of that one first. So you can find new game around line 62. Once we've done all the game setup, basically we need to publish our event. So here, after creating the player's trays, let's go ahead and publish our event. As anticipated, now we have all the information that we need here. We have the game, so we have the game ID, we have the player IDs, and we have the current player. All we need to do is make the call to publish new game. So let's do that. We're going to call publish new game. We're going to give it the game ID. We're going to give it the player IDs. And then we're going to give it the current player, which we're going to calculate here by taking it from the current player IDs at the current player index. This returns potentially an error, but we don't really care about handling that because we're going to return either the error or the game right here. Okay, so find the saveTurn function. It should be around line 210. Now here we're going to need to send the game ID, the turn, the scores, and the current player to our publish function. And we do have most of that here, but we don't have the scores yet. So let's think a second. Now we calculated the final scores at the end of the game. Maybe we can use the calculate scores function that we created then. It calculates and returns a map of each player to their current score. And while we might be able to think of more efficient methods of accumulating the score data, they will certainly do it for now. So we'll call calculate scores and then pass all the information that we now have to publish and turn. The game ID, turn, scores, and current player. Let's do that right here. All we need to do is call that same function that we already wrote. We'll give it the game ID so it can calculate that, and it will return the scores to us. Obviously, if there's an error, we return the error. Otherwise, now we have everything that we need to call publish and turn. We have the game ID, we have the turn, we have the scores, we have the current player. And it's going to return potentially an error to us. And all we need to do here is return the error and the turn. So either one is fine. Okay, not too bad. So let's go to the next one. Now find the function gameOver. It should be around line 303. After we calculate the scores for the leaderboard, we need to publish the end game event. So we need the game ID, the last turn, and, well, actually, here we don't have the last turn. Okay, no problem. We've been here before. We have a getLastTurn method already. We can call that. We'll get the last turn from there. We'll pass the game ID, turn, and scores to the publish end game function. That should be easy enough, but let's go ahead and do that. So here we'll call getLastTurn. We have the game ID, so we'll pass it that. It will return a turn to us. If there's an error, we get out. Otherwise, we'll publish the end game. Game ID, turn, scores, and that's all we need. One more time, and we have 3 passing tests. Excellent. I'm good to move on. Hopefully you are as well. If not, well, programming is problem solving, so don't worry, you'll get it. So we're almost there. In the next video, we'll subscribe to our new events, and we'll complete the circle of life for our game. Video 9.4, subscribing to the events. So now we've created our events and published them to a Redis channel. In this video, we'll code a simple function that allows us to subscribe to the pub/sub mechanism to watch a game as it's being played. Okay, let's check out the 9.4 branch. And now we're going to edit a file. This time we're going to edit a file in the bin directory called wordfling. Now take a look at the bottom, line 127 or so. Look at the watch game function. We're going to add code here that prints out what's happening in a game as it happens by listening to the pub/sub events that we're raising in the Redis database. So the first thing I want you to see here is we're going to connect to Redis, and this is going to be based on just a parameter that we pass in. So I've already done it for you, but it will either connect to the test database when we're running our tests, or it will connect to the normal database, just depending on our configuration. So the first thing we'll do after that is we're going to set up a message handler. Now we're going to use the psubscribe Redis command that we discussed a couple of videos ago to subscribe to the channel. So we're going to then listen on the Redis pMessage event queue. This queue will call our handler function with the pattern, the channel, and the message. Now we don't especially care about the pattern, but the channel will tell us the game ID and will parse the message as a JSON object and print both the ID and the event name to the console. So let's do that. We already have our Redis connection, so let's call Redis on pMessage. As we said, this function is going to return to us a pattern, the channel that we're on, and a message. Now in this, we're just going to call the function that I already created for you called formatMessage, rather than typing everything out again. And actually we need to make a small modification. Instead, we're taking the message here, but we also need the channel. Okay. So that's going to format the message, and as you can see, what it's going to do, it has to parse the message into an object. Then, based on the type of event, it's either going to print the new game, the end turn, or the end game information. In the case of a new game, you can see that it's getting the player's scores and printing those. In the case of end turn, it's getting the last turn player ID, the word, and the score, and then printing all the players' scores. And in the case of endgame, it's getting the players' scores from the message. So let's finish our work here and actually subscribe to that. We're going to call Redis p subscribe, and it's going to be game : as we decided, and then the game ID that we pass in. And I'm just going to put a little message here that we're watching the game and which game we're watching so that we can see it on the console when we start. Okay, great. Now one thing to note is that since we're using psubscribe, we're actually passing in a pattern. So we can actually even accept a star or an asterisk to be able to display all the games that are running if we want, and we don't have to choose one. In fact, let's go ahead and do that. Now we're going to execute node bin wordfling, and we're going to execute the watch game command that I have in that file. We're going to pass it a star in quotes, that's required, and then pass it the test option so that it runs against our test database. And we get our watching game. Now let's switch to another terminal and go ahead and run those tests that we ran a second ago. Great, our tests ran fine. So now let's go back over and look and see what's happened on the other side. As you can see, now a game has actually been played. Now, true, it's not a very interesting game, and it's not even being played with valid words. If you look, you'd see I cheated a little bit in the tests on what actually is a valid word. But it is truly a game in the sense that we've started a game, we've played some turns, and we have ended a game. In fact, if you run the entire test suite by using npm test, now you can watch and see that several games are being started, many turns are taken, and some games are completed during the course of our tests. I'll show you that here. This will run the entire test suite, all the games. And if you go back and look at your transcript, you can see over and over that several games are being played. So that's it for this section. You now know how the Redis publish-subscribe model works and have integrated the publishing of events into our game. Also, we have subscribed to events in a separate process. We've only scratched the surface of this very powerful feature, and I hope you'll now take this idea to create a true interactive client of the game that you and your friends can play. So we've done it. We've implemented the entire back-end system of a game. We're going to wrap up in the next section. Section 10, wrapping up. You've worked with many of the Redis data structures, and now you have an entire game at your disposal. In this section, we'll look at what you've learned so far, and we'll talk a little bit about what you could do next. Video 10.1, what have you learned? In this video, we'll talk about what we've covered in this course and what you've learned about Redis. We'll review what Redis is and the ways we've used it, and the data structures we've used to create our game. First of all, let's recall what Redis really is. It's an open source, in-memory, networked key value store. It's a simple definition, but it has several specific implications for its use. As a key value store, one expects that a primary access will be via keys, not queries. And as we've seen, Redis doesn't provide much of a query mechanism and has no support for secondary indexes. In addition, because data is in memory, we must ensure that we have enough memory on hand to hold our database. That said, it is networked and durable, which means that we can store the data itself on a local or remote disk and load it again as needed later. All in all, extremely useful for the right applications. We've also learned how to install, connect to, and manipulate Redis. We've covered installing the system from packages and source. We've covered connecting to Redis locally, remotely, and with and without password protection. And we've explored using the Redis command line interface. Finally, of course, we've extensively used Node.js to connect to and manipulate the Redis data structures to create a game. And finally, we've explored several Redis data structures. We've used Redis at its most basic, as a simple key value system. We've also used a Redis list to store unordered data elements. We used the Redis set to store unordered, non-duplicate information and explored its capabilities to quickly combine sets using intersection, union, and difference. We've further explored the sorted set data structure as a way of imposing order onto a set based on a score that we gave the data elements and used it to create a leaderboard for our game. And finally, we looked at the pub/sub capabilities of Redis to see how one client of Redis can receive events raised by other clients. As you can see, we've covered quite a bit, but in the next video, we'll look at what we didn't do and where you might take things from here. Welcome to the final video of this course, video 10.2, What More Could Be Done? Or, put another way, what didn't we do? In this video, we'll talk briefly about what features we didn't cover in Redis and what you may want to investigate on your own. And we'll talk about what we didn't do in the game that you may want to take on as an exercise for the student. First off, what didn't we cover in Redis? Well, we covered a lot, but there's certainly more advanced topics that could be covered. For example, Redis has the ability to treat a string as a bitmap. It's not really another data type, but it's just a way of manipulating strings into storing bits of information in a very compact manner. Also, a real Redis data type we didn't cover is the hyperlog log. Now, similar to a set, this is a way to have a very compact representation of information. But in this case, it's not like a set in that it just estimates cardinality. It can be useful for counters that don't need to be 100% accurate, for example. Now, we didn't cover Lua scripts. Lua is a programming language that can be used to perform the equivalent of stored procedures. In other words, execution within the Redis database itself instead of on the client. We also didn't cover transactions, which allow a client to execute a group of commands atomically. And finally, since we were focused on development, we didn't cover anything related to deployment and tuning of a production database. Wow, there is always more to learn. Finally, what didn't we do with the game? Well, I'm sure you already noticed, we don't have a user interface for the game, and not even a text-based one. But I have every confidence in your ability to add one. All the core work is done now. Maybe a web app would be nice. What else? Well, we have no social features. Nobody can have a conversation over a game or do any trash talking. You might consider how utilizing the Redis pub/sub capabilities could enable this. Also, hopefully when I mentioned Redis transactions, you thought to yourself, hey, we probably should have used those in the game. And yep, we probably should have. Since I have all the tests in place to ensure the functionality, maybe you want to have a go at using the multi command and protecting the game from partially executed items. If you remember, there is one example in there already. And finally, one thing we didn't do, evaluate other data stores to see if they might be more appropriate for our game. If I were going to publish this game for real, I would want to be sure that Redis was the appropriate choice for all of my features, given my functional and scalability needs. And with that, we've come to the end of this course. I really hope that you enjoyed playing along and have learned some valuable Redis skills. Perhaps some Node.js skills, and maybe even some game development skills. And while it may be game over for this course, the learning is lifelong. Enjoy!